Um, so it's week 6. There is a quiz tomorrow. I know it's like I'm the bearer of bad news too. So there is a quiz tomorrow covering chapter 6, including the stuff I covered today. I will post some practice problems online, which I think will be very reflective of what the quiz will look like. So there will be some practice problems. If you can get through the practice problems, then you'll be fine for the quiz, okay? Okay, so we left off on Friday talking about the binomial distribution. Okay. And this is probably already in your notes, but I will rehash it today just to put today's lesson in context, I guess. So for the binomial distribution, we repeat a random trial n times. Okay. Each trial has 2 possible outcomes. We can have a, quote, success with probability p, and we can have a failure with probability 1 minus p. Each trial is independent of the other. Of the other trials, or the others. And we are interested in seeing n successes. Or in the probability of x, wait, what did I say? In the probability of x successes. Okay? All right, and so one thing to note is that for binomial problems, the order of, or the sequence, the order of the outcomes does not matter. Okay, so we are interested only in getting x successes. So if the question says, what is the probability you flip heads, then tails, then tails, okay? Because here this has an order of outcomes. It has to go heads, then tails, then tails. This is not binomial, okay? So it has to go heads, then tails, okay? Over here, if I say, what is the probability you flip heads once and tails twice, or even if I just say heads once out of 3 flips, this is binomial, okay? I don't even have to say that you flip tails twice, because flipping heads once necessitates that tails has to land twice, right? Because so saying heads once equals getting tails twice. All right, and in this situation, we can have heads, tails, tails, or heads. Or tails, heads, tails, or tails, tails, heads. Okay, so in this case, any of these arrangements is allowed. So this one is binomial, whereas the other one is not binomial. So it will be important that you can distinguish between problems that are and are not binomial. Okay, and so the key distinction between kind of similar sounding problems is that you ask, does the order matter in these circumstances? Okay, so let's get into calculating the probabilities of certain of these types of problems. Okay, can I flip to the next slide? More or less, yes? Okay. So let's say I have a special coin here. Okay, and the special coin will land heads with probability equal to 0.7, okay? Which, you should be able to figure out then that probability of tails will be what? 0.3, okay? So that, the problem will often just write probability of heads 0.7 or probability of this outcome is 0.7 and you got to figure the other side out. Okay. All right, so we will flip the coin 4 times. Okay, and I'm going to ask, what is the probability that the coin will land heads 2 times? Okay, and if it lands heads 2 times, that implies it landed tails how many times? All right, so to answer this, I'm going to list all possible arrangements. Bless you. Okay, so we're going to list all possible arrangements. So we want heads, 2 heads and 2 tails, right? Okay, so we can have heads, heads, tails, tails, heads, tails, heads, tails, heads, tails, tails, heads, tails, heads, tails, heads, and tails, heads, heads, tails. Okay? I'm pretty sure I've gotten them all. Okay. All right, and so let's figure out the probability for this one. So the probability is going to equal, so this exact sequence is going to be 0.7 for heads on the first times 0.7 times tails will be 0.3 and tails will be 0.3, right? And so collapsing this or just grouping terms together, I got 0.7 squared times 0.3 squared. Good? Okay, the next one, if we list off the probabilities, we got heads, tails, so it's going to be 0.7, and then tails is 0.3, times heads, which is 0.7, times tails, which is 0.3. Okay, so heads, tails, tails. Okay, and again, if I group the like terms together, I still have 0.7 squared and 0.3 squared. The next one, I'll just do this one to be a little bit pedantic, is going to be 0.7, and then tails 0.3 times probability of tails, also 0.3, times the probability of heads, 0.7. Okay, so we also have 0.7 squared, times 0.3 squared. Okay. And so all of these, I could go through and calculate the probabilities of 0.3 times 0.3 times 0.7, 0.7, but I hope it is clear that all of these will have the same probability of 0.7 squared and 0.3 squared. Are we in agreement there? Okay, for all of these possible arrangements. Okay. Okay, so excuse me. The when we ask what is the probability that the coin will land heads 2 times, we're really asking what's the probability that we get this outcome, heads, heads, tails, tails, or the probability we get this outcome, heads, tails, heads, tails, or the probability we get this one, heads, tails, tails, heads, or whatever. Okay, we're asking what's the probability we get one of these outcomes where heads occurred twice. Okay, and so whenever we have or probabilities, how do we put them together? We add them, right? So if we got A or B, we add them together, but we also subtract off any overlap. Okay. Is there any overlap between any of these events? No. You cannot have the outcome be heads, heads, tails, tails, and at the same time the outcome be heads, tails, heads, tails. Okay. They're like, if you get one of these outcomes, all of the other outcomes are not possible. Okay. So all of these outcomes are mutually exclusive, so we can just add them up. Okay, we don't have to worry about subtracting any overlap. Okay, so the total probability of getting heads twice is going to equal 0.7 squared times 0.3 squared. And there are 6 possible arrangements, so I'm going to multiply all of that by 6. Is that okay? And so when we do that in terms of the math, we do 6 times 0.7 squared times 0.3 squared. Oops. And I get 0.2646. Okay, so that is the probability that we flip the coin 4 times and we get heads twice. Okay, and heads twice means we got tails twice also. Is that okay? All right, so let's give you guys a problem, and we'll make a clicker problem out of this. So we have the same special coin. So probability of heads is still 0.7. We will flip the coin 4 times. And we want to know what is the probability of getting 3 heads. Okay, and so to get you started, I'd say list all possible arrangements, all arrangements. And so one is heads, 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 tails. Another will be heads, heads, tails, heads, and then you'll want to list off all other arrangements, okay? All right, and then let me list off answer choices here. Okay. Okay, so let's see. So new multiple choice problem. So go ahead and hear this out. Running lower than this. Okay, we'll just say just a few more seconds here. Just a few more seconds. But it looks like most of you have clicked, so all right, I'm going to hit stop. So click something if you haven't done so already. Okay, and let's see how you guys did. And that is the correct answer. Okay. Okay, and so again, we wanted to list off all possible arrangements. So that would include heads, tails, heads, heads, and tails, heads, heads, heads. Okay? So each of these has probability of heads 0.7 3 times and tails 0.3 1 time, okay? Which is 0.1029, okay? That's each of these, but there are 4 arrangements. So 4 arrangements. So a total probability equal to 4 times 0.7 to the third times 0.3 to the 1. So we have 0.4116. Okay, and that is our answer. Excellent. Okay, so the general form of our binomial, okay, so remember the binomial distribution, we should be able to identify n trials. P is the probability of success. And we want X successes. Okay. Which implies the probability of failure would be 1 minus P is the probability of failure. And we want how many failures? n minus x, right? If we have a total of n trials, we are going to need n minus x failures. Okay? So the general form of the binomial is going to be the number of arrangements times the probability of a success, p, raised to the x, because we want that to happen x times. So actually, let me change this to a dot. Okay, multiplied by 1 minus p, the probability of failure, raised to the n minus x, the number of failures that need to happen. Okay, and that's what we see when we, in this case, we have 4 flips, n is 4, the probability of getting 3 heads, so x is 3, and probability of heads is 0.7, so we see 0.7 raised to the third failure, 0.3 raised to the 1, so these two things add up to 4, and then we have 4 possible arrangements. Okay, so this is kind of the general form of the, binomial probability. Okay, sounds reasonable, right? Sounds reasonable to me, but of course it would. Okay, so the trick, or the I guess it gets complicated when we talk about the number of possible arrangements. Okay, so the number of arrangements, when we talked about 4 coin flips, it's not too hard to list off all the possible arrangements. Okay, but if I said something like, I'm going to flip the coin 10 times, and we want to know what's the probability of getting 5 heads, then it will be very tedious to try to list off all possible arrangements, right? So, let's say like 10 flips, and we want 5 heads. Okay, this, now it's very tedious to list all arrangements. Okay, and so I will just tell you that you can study what we call combinations, okay, or combinatorics, but we'll just call these combinations, and this is the exact problem that this thing solves. Okay, so it says, how many combinations are there where we have 10 things and we want to pick 5 of them. Okay, and so with this thing with 10 flips and 5 heads, we call this 10 choose 5. Okay, and it can also be written 10 choose 5 like this, okay, or 10C5, okay? And this is the exact answer. How many arrangements are there if you want to choose 5 out of 10? Okay, and so we call this, NCR, or N choose R, or NCR. And the formula is n factorial divided by r factorial divided by, or times n minus r factorial. Now, yeah, don't even really bother with this, okay? Okay, so don't bother, because probably your calculator has this. And if you don't have a calculator that can do this, it might be worth considering getting a calculator that can, or I'll probably list off some of these things. So on your calculator, look for an NCR button, Okay, if you have a Casio, it might be over the division key. It might be somewhere on your keyboard. Other things is you might have to hit a math button or a PRB for probability button, okay? And then you use the menu to find NCR, okay? So you might have to find the little math button or the probability button, okay? And use the menus to navigate to NCR, okay? And so on my calculator, if I type in 10 and I hit Shift Divide key 5, it says 252. So 10 choose 5 is equal to 252. This says if if there are 10 things, 10 coin flips, and you need to choose 5 of them to be heads, there are 252 ways for this to happen. Okay? So that handles this problem of dealing with all of these possible arrangements. Where if you were given the task to list off all 252, it would be quite challenging, I think. Okay, are you guys able to find this on your calculators? Kinda, maybe. Okay, well, we should figure this out, and then so one thing to note is that if you do 10 choose 6, you'll get 210. Okay, I'll show you. 10 choose 6 is 210. Okay, and if I do 10 choose 4, I also get 210. Okay. Okay, and so what's going on here? Okay. Well, I mean, if you look at the formula, then it's like, oh, okay, well, yeah, but then intuitively, what's going on? So we can think of this, I call this the Taco Bell or midnight problem. So let's say you're hanging out. There's 10 of you hanging out together, and suddenly you guys get hungry and you say, we must have Taco Bell right now. But only 4 people can fit in my car, and or fit in the car, and we're not going to send everybody. So the 4 of you go get food and bring it back. How many ways are there to pick 4 people out of 10 to make the trip to Taco Bell? Okay. Well, it turns out there's 210 possible arrangements. Okay, assuming it doesn't really matter who's driving or who gets in the car. There's 210 ways to pick 4 people to go to Taco Bell. But if you think about it, choosing 4 people to go is the exact same thing as choosing 6 people to stay behind. Okay, so the answer for who gets to go is implicitly the same thing as the answer to who has to stay behind. Okay, so choosing 4 out of 10 to go to Taco Bell or whatever place you decide to eat is the same as choosing 6 out of 10 to stay behind. Okay, so we have that. Okay, so let's try. Let's go back to our basketball friend, Steph Curry. All right. So we'll say, Steph Curry is a 90% free throw shooter, meaning each time he takes a free throw, he has a 90% chance of making it. All right, and then we will assume each free throw is independent. So we'll say he takes 8 free throws in a game. We'll say each shot is independent, which may or may not be true in real life. But for the sake of this problem, we will assume that it is. Each shot is independent. Okay, and I'm going to ask, what is the probability he makes at least 7 throws? Okay, so the key there is at least 7. Okay, so I recommend listing off your n, p, and x for this problem. Okay, and I will list off fake answer choices here. One of these will be correct, and we'll figure this out. Okay, so let me list off some answer choices here. So go ahead and try this out. I guess I'll list off and I'll say 8 choose 8 is equal to 1. 8 choose 7 is equal to 8. 8 choose 6 is equal to 28. In case you don't have these buttons on your calculator. Okay, you can discuss with your neighbors as well. How are we doing? Yeah. Keep a working. All right, we'll say 20 more seconds here. Okay, 10 more seconds. All right, just start clicking, do your best. Okay, I'm gonna go ahead and hit stop here. And okay, well we'll go through the problem together. Okay, so we have n is equal to 8, p is equal to 0.9, right? And here it says, what's the probability he makes at least 7 free throws? So our x is going to be 7 or 8, right? Because when we say at least 7, that means 7 or more. So 7 or 8, and if you're taking 8 free throws, the most you can make is 8 out of 8. Okay. All right, and so we'll calculate each of these things. So the probability for making 7 is going to be 8 choose 7. And probability of 0.9, that has to happen 7 times. So the probability of his success making the free throw is 0.9. It has to happen 7 times, but that means he also has to miss it 1 time. So 0.1 raised to the 1. Okay. And then we also want the probability that he makes all 8 out of 8. So that's going to be 8 choose 8. And we're going to have 0.9 raised to the 8 power, and 0.1 raised to the 0. Okay, and I just want to make sure this part is okay with it, all of you. Okay, well, I'm getting head nods from most of you, and then the rest of you I'm just going to assume is okay. So when you calculate this out, you get 0.3826. Okay. If you did not include this part, you would get 0.0478. And then this part, 8 out of 8, is going to be 0.4305. So when you add these two together, you get 0.8131, and that is our answer. Okay, so it looks like a lot of you guys got it, okay, but some of you missed. Is that good? So far, so good? Okay. What happened? Point. Which one? I'm sorry. 0.1 to the 1? Yeah, okay, because if he's going to make it 7 times out of 8, that means if he's taking 8 shots and he's made 7 of them, it means he must have missed once, okay? Like, you can't just say he made 7 shots and then there's this mystery about the last shot, okay? It says he must have missed that one if he has a total of 8 shots, okay? So you can't just leave it off, okay? Okay, so we have that. There's a interesting relationship. So when we say if we asked a question, what is the probability he misses 2 or more shots? Okay, this is written in terms of misses here. Okay, right now our probability is in the terms of him making it. So what we have to do, if you see a problem written like this, you have to kind of rewrite the problem in terms of making, in terms of shots made. So yeah, what is the probability he makes, what, 2 or more misses is making 6 shots or fewer. okay? And then it becomes a problem that we can solve. Okay, and so here we would have x is equal to 6, 5, 4, 3, 2, 1, and 0, okay? Now this would actually be quite tedious for us to calculate. We could do it. It would be 8 choose 6, blah, 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 plus 8 choose 5, plus 8 choose 4, all the way down to 8 choose 0, okay? Now, we don't want to do that. So the probability of 6 or fewer is going to equal 1 minus the probability of 7 or more. Now, why is that? Well, if we list off all outcomes, okay, we have 0. This is the number of shots you can make. Okay. When a person takes 8 basketball shots, one of these outcomes is going to happen. He either makes 8 or 7 or 6 or all the way down to 0. One of these things is going to happen. So all of these things have to add up to 1. Okay? So the total probability of all outcomes will add up to 1. Okay? So if we are interested in making 6 or fewer, we could calculate 6 or fewer, or we can calculate 7 or 8. Okay? We are actually already calculated this, and we know this probability is equal to point, what was it, 8161 or something like that? What was that? 8131? Okay, 8131 is what we said. Okay, and so that must mean all of this other stuff has to add up to 1 minus that is 0.1869, okay? Because everything has to add up to 1. Okay, so what's the probability he misses 2 or more shots? It happens about 18-19% of the time. Okay, is that good? Okay, so there's one last key thing, and this will come in the future, and I don't really have much explanation behind it, other than the mean of a binomial distribution is going to be n times p. Okay, and this kind of makes intuitive sense. If you do something 10 times and the probability of success is 0.7, you expect on average 70% out of 10 or 7 successes on average. So this is kind of like the average number of successes. The mean is this. The standard deviation of the binomial distribution is going to be equal to the square root of n times p times 1 minus p, okay? And I don't have an easy explanation for this. If we were in a higher level stats class, we could talk about this, but as far as this class goes, I'm just going to say this is what it is. You got to know this, okay? And you know, I don't really like to do that very often, but in this circumstance, this is an important relationship that you got to know. So just learn that standard deviation of a binomial is n times p times 1 minus p. Okay, it'll come back later. So, all right, I'll post up some practice problems for tomorrow's quiz. You can look forward to that on tonight. Okay, so we'll see you guys.